Hi everyone, welcome back. In this particular video, we're going to start talking about the chemistry of nitriles. Now, nitriles, although they look very different from carboxylic acid derivatives, their chemistry is very similar to them. And that's partly because in the nitrile, you have a carbon which has three bonds to a hetero atom. That is an atom that's not a carbon or a hydrogen here. And compare that to like the ester, for example, or any other carboxylic acid derivative. What you notice is that the acyl carbon here has two bonds to the acyl oxygen, and it has a single bond to the ester oxygen. So that's a total of three bonds to a hetero atom. And that is pretty much what you see in the nitrile. So that's why nitriles, their chemistry is similar to those of carboxylic acid derivatives. As far as the preparation of nitriles is concerned, they're most conveniently prepared from alkyl halides. So if you have an alkyl halide, you can react it with sodium cyanide to get the nitrile product. Now, this reaction mechanistically is an SN2 reaction. So the cyanide comes and attacks the alpha carbon in the alkyl halide with the simultaneous loss of the halogen. So it's a concerted process. This is an SN2 attack. And since this is an SN2 attack, everything that we know about SN2 reaction applies here, which means tertiary alkyl halides cannot be converted to nitriles using this chemistry, but primary and secondary alkyl halides should work fine. So alkyl halides, when they react with sodium cyanide, they're converted into the alkyl nitrile. Another method for synthesizing or preparing nitriles starts from primary amides. Primary amides can be converted into nitriles by reacting with thionyl chloride, SOCl2, under heating, okay, or with heating. So when a primary amide, now that's specific, when a primary amide reacts with thionyl chloride, it is converted into an alkyl nitrile, along with byproducts sulfur dioxide and HCl. The mechanism of this reaction involves an initial attack by the primary amide on thionyl chloride. Now, this attack is reminiscent of other nucleophilic attacks by carboxylic acid derivatives, specifically reactions where we've involved thionyl chloride, which was maybe the reaction of a carboxylic acid with thionyl chloride to make the acid chloride compound. So I'm going to use the nitrogen lone pair here to do some resonance and attack the sulfur. The sulfur is attacked by this acyl oxygen. We're just using the nitrogen lone pair to do some resonance and draw the next intermediate here. So as the sulfur is attacked, the double bond here gets moved over, and it would bring us to the next intermediate, which is going to be double bond N, H2 here, O sulfur, single bond to the oxygen, negative charge, with two chlorines on the sulfur. So that would be our next intermediate. And from here, as far as the sulfur is concerned, this intermediate is almost like a tetrahedral intermediate, and there should be a formal positive charge on that nitrogen atom, two lone pairs on the oxygen. So this intermediate, like I was saying, is almost like a tetrahedral intermediate. And so what this does is the oxygen brings its lone pair back to form the double bond, reform the double bond, and simultaneously one of these chlorines is kicked out. Okay, that acts as a leaving group. That would take us to the next intermediate, where we have oxygen connected to sulfur, double bonded to an oxygen with chlorine, two lone pairs on that oxygen, two lone pairs on this oxygen, and then we have a nitrogen with a formal positive charge and two hydrogens on it. And now from here, some base in the system, and this will be weak base. So any species here which can act as a base, this base can deprotonate the nitrogen here. Okay, remove a proton on that nitrogen. That's going to give the electrons back to the nitrogen atom. It's going to bring us to the next intermediate here, where we would have a double bond nitrogen, hydrogen, and a lone pair on the hydrogen. And along with that, we will have the protonated base. Okay, the base is now protonated. And now from this intermediate, one last step, because we have to form the triple bond between the carbon and the nitrogen, and that's this carbon and that nitrogen. Another molecule of base that is present in the system can go ahead and deprotonate this hydrogen. As that happens, the bond between the nitrogen and the hydrogen becomes the triple bond between the carbon and the nitrogen. Simultaneously, the leaving group here leaves. So the oxygen-carbon bond breaks. You get a double bond between sulfur, and that would kick out a chlorine. So a couple of electron pushes happening simultaneously over here. The base deprotonates this imine, actually. The imine gets deprotonated. You form the triple bond between carbon and nitrogen. The bond between carbon and oxygen breaks. You get a double bond between sulfur and oxygen, and the chloride is kicked out. So when you draw it out, finally, what you've made is you've made the nitrile. So we've converted the primary amide here into the nitrile, along with sulfur dioxide and chloride. And plus, you have the base that's now protonated. So the base is now, it does have a proton. So we made a nitrile here. So if you look at it overall in this mechanism, what we've done is we've converted the primary amide into an alkyl nitrile. Simultaneously, we've made sulfur dioxide. So that's one of our byproducts. And we lost 2 chlorides. So there's a loss of chloride here. So I can show that here. So there is 1 chloride lost over there. There's another chloride lost in this last step. And there are 2 protons that are removed. So overall, that's 2 HCl molecules. So that's the mechanism for the conversion of a primary amide into an alkyl nitrile. Another method to synthesize these molecules, alkyl nitriles.